Hello, hi everyone. I hope I am live. Yep. Okay. So today we are going to talk about this is our second workshop for today, and we are going to talk about time series analysis and more about anomaly detection and time series analysis. So before I further jump into my workshop, how many of us have really worked before in time series? How many of us here have worked on time series? Let's say. Hi, Timothy. Hey, so I hope you guys can hear me, right? Great, awesome. So it seems like there are around, okay, awesome, one project. Okay, all right. So how many of us have worked on anomaly detection, detecting the anomalies in a data set? Google stock pricing. Oh, yeah, that is certainly time series. Yeah. So how many of us have worked on anomaly detection, detecting anomalies or outliers, let's say? Okay, all right. So today what we are going to do is we are going to combine anomaly and time series, and we are going to find out a method, a technique that we can use to detect outliers or anomalies in a time series analysis, right? So let me share my screen, and I think it will be a bit difficult because I'll have to keep coming back to the screen to answer your questions, but I'll manage anyway. Okay, awesome. So let me share my screen, and then we'll start. One moment here. Okay, so as the topic for today is anomaly detection. About me, I'm a deep learning researcher at pulpvision.ai, which is a deep tech AI startup wherein we build enterprise and industrial AI products for a lot of Fortune 500 companies. Now, what is time series essentially? Every data set which has a time component associated with it is known as a time series data set, right? So it could be anything from a simple temperature data. For example, if we are recording temperature of every day for the coming month, so it will be temperature of 30 days, right? So this is a time series data wherein we have data of every single day. So every data set wherein a time component is involved is basically a time series. There are many examples for it. One is temperature. The other one could be stock prices, crypto prices. Then we can also have sales of a particular company on a particular day, right? So and sales of that company on every day for the coming year or 2 years, right? So that would also be a time series data. So there are many multitude of examples of time series data essentially. Now, what is an anomaly? An anomaly is a different data point in a normal setting. So anything that is different from a normal data is known as an anomaly. So for example, if we look at this distribution, let me bring my pointer here. Okay, so I hope this pointer is visible. Yeah, okay. So if you look at this data set, this is the normal data distribution, right? And then there is one point which is here, which is more like an outlier. Then there are few points here, there are few here, and then here, and then here. So these are all a bunch of outliers, which we call as a different from the normal data, which is this distribution. Similarly here, there is this what we can say as data, although it is already not very regular. There is already a lot of variation in this data set, but still I think this one really goes beyond the limits, right? And definitely this seems to be an anomaly here, right? So these were some some examples of anomaly. Anomaly would not be very clear to you every time. For example, in this time, this point is not very clear to you because some of us might discuss or debate that this point also might be an anomaly, right? So anomalies are controversial sometimes, and it totally depends upon data set to data set what could be an anomaly and what could not be an anomaly, and also it depends upon the business expertise in a way. Yeah. Okay. So far, I don't think you guys would have any questions. So let's move ahead to finding the methods there are for detecting the anomalies. So the first and the most fundamental method is analyzing the data. The data set, we plot it, we visualize it, and we see if there could be any anomalies there. So for example, this method, we visualize this and we see if there could be any anomalies in the data set. This is the most fundamental one in a way, but this does not help us if, let's say, there are a billion data points with us. If let's say there are billion rows in the data set, we cannot visualize those billion data points, right? It becomes too tedious for the computer to plot a billion points, right? And definitely on a desktop or a laptop, it becomes very difficult. So it's not practical to use the visualization or the manual analysis method to detect the anomalies when we have a huge data set. But when we have a very small data set, you can definitely do that. And it is, I would say, a very good, yeah.
We can't see your slides right now.
Oh, yeah.
So, perfect.
Yeah, my bad, guys.
Thank you.
Okay, so my bad. Let me bring up a pointer here. And so I was talking about this particular slide here, wherein, yep. But this particular image here, these are the anomalies. Like this point here is an anomaly. This is an anomaly. This is an anomaly, right? And similarly, in this particular image, although it's kind of controversial because some of you might debate that this is also an anomaly, but still I would say that this goes beyond what a normal limit of a data could be, right? So these are just very I would say controversial examples of anomalies. There are some examples which are very clear. There are some cases which are kind of not so clear in a lot of cases, right? So coming to the methods of anomaly detection, we have the first one is analyzing the data, which is just manually analyzing the data, right? So for example, if this is the data set, we have plotted this, we have visualized this, and we have got the distribution in a way, right? And we can manually analyze this, like this seems to be an anomaly, this seems to be an anomaly, and this seems to be an anomaly, right? So this is the first and the foremost method, which I think we all do that. We analyze the data set manually in a way, right? The second method is basically to find a central tendency. And what do we mean by a central tendency essentially? Anybody in the chat who can tell me what do we mean by central tendencies? Anyone? So essentially central tendencies mean the mean median mode of the data, right? So for example, if you look at this data set, most of the data points belong in the center, right? And if we calculate the mean or the median of this particular distribution, it will definitely pass through the middle line here. Yeah. And now the mean or the median will definitely pass through the middle line here. And if we take a standard deviation of this particular data, a +1 sigma, which is +1 standard deviation above the median and -1 standard deviation below the median, I think would probably lie in this ratio, wherein it would be something like this. Like this would become the +1 standard deviation, this would become the -1 standard deviation, and the middle line would be the median or the mean in a way, right? And any point, we can consider this as any point which is above or below the mean could be considered as an anomaly. Although in this case, this is more like, it does not seem like this data set has any anomaly because it is like this only. And if we had any very high peak voltage, let's say here, from here till here, then we would have said that that could be an anomaly, right? But if we use the same method with the median and plus minus standard deviation, here we could have found out these anomalies, right? So the second method essentially is to find the data points which are away from ±1, 2, or 3 standard deviations from the median. Essentially, normally we consider 3 deviations away from the mean, but in some cases, I would say +4 deviations away would also be considered as fair in a way. I hope this point is clear. Wherein how can we find out the outliers or anomalies away from the mean median mode, right? Which is basically by using the central tendency method. Yep. All right. So the next thing is clustering. Now, this is a very interesting example that I have for you. This dataset belongs to a very famous e-commerce merchant, which is known as Cadbury. Now, if you notice, this is on the x-axis we have dates, and on the y-axis we have sales of a particular product. There are multiple lines in the graph, and each line corresponds to a particular product that you can see here. Right, so the purple line here corresponds to Celebration Assorted Chocolate Gift Pack. And then the red line corresponds to Celebration Assorted Pack, which is 180 grams, and purple one is 146 grams, right? So essentially what you notice here is that when we start in Jan of 2018, all the sales of all the products were just similar, which was not so much, right? And if you notice, they are increasing parallelly. It's not that one product is selling in a particular month and a different product is selling in a different month. It's like all the products are selling together. When the sales of one product is increasing, the sales of other product is also increasing, because it's like a very high correlation between these selling patterns. If you notice, in this month, all of the sales of all the product increases. All the rate at which that increase was different, but they increased parallelly, simultaneously, and they decreased also simultaneously at this, or at almost the same rates at which they increased, right? And if you can notice at different sections that there is a very high correlation in the sales pattern of this particular distribution. And why do you think is that? Any ideas or any feeling that you get when you see this data? I've already told you this belongs to sales of a chocolate. In fact, sales of different kinds of chocolate from a particular vendor. And this is the data that we have. Now, what are your ideas why this pattern might be there? What do you think about this? Holidays, okay. Nice one. But if in holidays, festival, seasonality, yeah, that definitely there is a seasonality. But essentially, what is the reason behind that seasonality? If you notice, in countries where there is different weathers, Valentine. Oh yeah, that's a very interesting point by someone, which is Valentine's Day. So yeah, this peak here belongs to this here. This peak essentially belongs to Valentine. Yeah, this seems low, but when you notice 9 1 11 1 2020 Feb, essentially here, and then here we have some peak, which is 2019 Feb, we have a peak here. In 2020, we don't have much of a peak. In 2018, we don't have much of a peak, but in 2019, we have a good peak. And the reason is essentially because I think this data also comes from the offline stores, and it was the COVID period in 2020, and that's why people did not went out to buy these chocolates in a way. But yeah, it's a very interesting point that the sales of a chocolate would go up in the month of Feb, and we would have to see that pattern, but we don't see it, and then we will have to find out the reasons why it's not there. So that's an interesting way of. Halloween is in October, advertising one of those for Halloween vacation season. Yeah. So I think you got the point what I'm trying to put in here. Like, it could be either Halloween, it could be Valentine's, it could be a sales season, it could be a festive season, right? If you notice, it's this month, which is the 10th, October. So October month of 2019 has the maximum sales, and actually the thing is, in October, the data, this belongs to a particular country, and in that country, we have a very big festival in the month of October, and that's why the sales went so crazy in the month of October, right? So that's the reason why we have so much sales in October. And then if you notice again here in October, right, this here also sales went very high. So October seems to be and this pattern seems to repeat if you notice. So October, and then a couple of months before October, there are like two peaks here, and similarly there are two peaks here. And every year this is the same pattern. It seems like in the month of October and 2 months before that, there are two peaks that we get, consecutive peaks. Yeah. So this is how we can understand and make sense out of time series data. Now, coming to the clustering part, how we can use clustering to find the anomalies in the data set. So essentially, if you notice, these all data points are very correlated to one another in a way, right? But in a way, if you notice this point here, would you say this is an anomaly? What do you think? This red point here, do you think is an anomaly? This one. Now, would you consider this as an anomaly? Because all the other sales charts of other products are also following a very similar pattern. So essentially, we cannot say this is an anomaly. Maybe we can clip it to a little low, but essentially, still, this would not be considered as an anomaly because every other product is also following the same pattern. Let's say let's say all the other products were following a different pattern, but one single product which usually follows the same pattern but in some month followed a different pattern. Now that would be considered as an anomaly. So essentially the point I'm trying to make is that when we cluster similar points together in such a scenario where there is a highly correlated data set and then there are some points which on particular dates on particular time it does not correlates well, that point at that particular date can be considered as an anomaly. Make sense? Yeah, FB profit is good. Yeah, exactly, Diwali in India. Great. So what do you think about clustering as a method? So what I was trying to tell you is that when we have a very high correlation and all the points move very closely to each other in a very similar manner, we cannot say that there are anomalies, right? But if we notice that there is one point which usually there is the sales of a particular product on all the different months, it is following the same pattern, but on a particular month in a particular year, not in every year, but on a particular year, it follows a different pattern. Either we find out the reason for that, and even if there is a reason, we don't want our model to ingest or absorb the wrong information of that anomaly, right? So what we do is we artificially remove that anomaly and make it as the other patterns are there. So for example, I'll give you an example that if let's say although this red is following the pattern which others are, which is the red has a similar pattern as the brown one, but let's say this red one had a different pattern. So let's say all the others would have been decreasing, only the red one would have been increasing, which is on this year only, not every year, only this year. So this point would be considered as an outlier because usually this does not happen every year. This does not happen. This happened only this year, right? And when you train a model and the model's responsibility is to forecast the next couple of months, 3 months, 5 months, 6 months forecast, if we feed in this anomalous data which might have occurred due to any reason, let's say because of the surroundings, because of any viral marketing campaign which could have happened due to any reason, next year also it would predict a very high sales of this product, which essentially would not be the correct way to predict because what happened this year might not happen the next year. So before building the model, this is using clustering. This is how we detect different points which are different from the rest of the sales patterns. Make sense? So this is you get this point, right? ETL, is it bad data packet? I assume usually ETL does not gives a bad data packet, but we can have such kind of erroneous results. Uh, we can have such kind of erroneous results when we visualize the data, especially in terms of inventory forecasting, sales forecasting. Yeah. Okay. All right. So I mean, yeah, you can try that threshold and residual. You can try that. Again, it totally depends upon data to data, but it is not a very static technique for every data set. Yeah. Now, and then there are the very complicated autoencoders. Now, autoencoders are something which is state of the art. They are very good at what they do, but there are a lot of limitations with respect to autoencoders. So first of all, they need a lot of data to train themselves, and usually we don't have such data. For example, let's say you have an e-commerce company which you have started 2 or 3 years ago. You only have 3 years of data. Now autoencoders require a lot of data, and they usually don't work well if they have, let's say, 2 years, 3 years, 4 years, 5 years of data. Companies which are very old, for example, Amazon can use their data, can use autoencoders for their data forecasting because they have huge data sets, right? From so many years they are working on. So essentially, we need a lot of data first of all for autoencoders, and then even if you have a lot of data, you need. There are different challenges when it comes to autoencoders. So only if you train it the right way, you'll get the right kind of results, and those results could be awesome, they could be impeccable, but it requires a lot of expertise to train the autoencoders in a way. Yeah, so autoencoders are great for experts, and only if you have a lot of data. Now, coming to the matrix profile, which is actually the topic for today, which I wanted to discuss with you, which is matrix profile. This is the most simplest method, the most fundamental method that you will find ever to detect an anomaly in a time series analysis, or just simply any data set, which is, it could, if there are any patterns in the data set, you would be able to find this using the matrix profile. Starting with this, let's say you have a time series data. Okay, so this is a series of data points, and if we plot this, this is what we get: 0, 1, 3, 2, 9, so on and so forth, right? So this is a time series data with length 13. Okay, now let's consider a particular subsequence of 2 elements, right? If we have considered subsequence of 2 elements, we'll make a group of these 2 numbers, and what we will do is we will keep sliding this. So the first subsequence becomes 0 and 1. Now we will slide this, so the second subsequence becomes 1 and 3. We will again slide this, the next subsequence becomes 3 and 2, and so on and so forth till the end, right? What happens is that essentially what we do is we calculate the Euclidean distance between every subsequence. So essentially, let's say, in this case, we took a subsequence of 2 elements. We can take a subsequence of 3 elements. We can also take a subsequence of 4 elements. This I will talk about later if you have any doubts with this. But let's say we take a subsequence of 4 elements here. Okay, so essentially what we do is, this is the subsequence that we took. We will slide this, and now the next subsequence is 1, 3, 2, 9. Now we have a vector which is 0, 1, 3, 2, and we have a vector which is 1, 3, 2, 9. We will calculate the Euclidean distance between these 2 vectors, okay, and then store it. Now what happens is that, so 0, 1, 3, 2, essentially 1, 3, 2, 9 was I was taking, but in this example we have taken 1, 2, 2, 10, which is also another subsequence. And how we calculate the distance? By simple Euclidean distance, which is like x1 minus x2 whole square plus minus y2 whole square plus so on and so forth, right? So this is simple. This is how we calculate the distance between a particular subsequence with every respective subsequence, right? So essentially, if we calculate this with every other subsequence, this is what the distance profile we get. So if we calculate the distance between this and itself, the distance is 0, right? If we calculate the distance between the first subsequence and the second one, which is 1, 3, 2, 9, the distance is this, which is 7.4. Then we calculate between this first one only and then the third subsequence, which is this 3, 2, 9, 1, and the distance is this, which is 6.9. And essentially we'll calculate for all the other subsequences there are, and we will get this as a distance profile. Yeah. So now what we do is, once we have this, we find out the smallest value that is there, which is 6.9. Right. So if we compare, if we find out the Euclidean distance of the first subsequence with every other subsequence, the smallest distance apart from 0, just ignore the 0 because it does not make sense, right? So apart from 0, the smallest distance is 6.9. Right. Similarly, if we calculate the distance of every subsequence with every other subsequence, we will get some distances. We will get n distances, right? So for example, the first row here, we have put an asterisk here just to ignore all the other distances and to just focus on the smallest distance, which is 6.9, as here. So the first row corresponds to when we find out the distance between the first subsequence and every other subsequence. The second row corresponds to when we find out the Euclidean distance between the second subsequence and the every other subsequence. And what is the minimum distance? It's 1.4. Similarly, the third row corresponds to the third subsequence and every other subsequence that is there, right? So when we have created this 2D matrix, we select the smallest distance from every row and we create a separate array, right? So now what we have is we started with this 1D array, and now we have this 1D array, which is known as a matrix profile, right? Very simple. We have just transformed this 1D array, which was a time series, into this by just calculating the Euclidean distance between every subsequence with every other subsequence. So far, everything is clear? Yep. So far, all said? Just let me know so that it makes the session more interesting. Yep. Okay. Any questions? Okay, so we have a question. Can you share? Oh yeah, definitely we'll share the slides. Yeah, definitely. All right, so I think, okay, awesome. All right. So far everything's clear, right? Okay, awesome. So the next thing is what we do is now let's see how this transformation can help us in a way. Yeah, so let's focus on the impact of using this matrix profile. Now, essentially, let's say this is the data that we got. Okay, so you see that this is the normal data, and then there is some anomalies here, and then there is some normal data again. Now, essentially, when we transform this input data, which is red, and we convert into a matrix profile, this is essentially what we get. Now, segregating this is a little difficult compared to segregating these areas, right? So essentially we transform this signal to this, and this becomes very easy to basically detect that. We can easily detect that there is some bad data here, right? And essentially at these intervals also, right? So the corresponding subsequence in the raw data at this location must have at least one similar point. So if we have to detect the anomaly in the data wherein it is difficult to detect, we can just convert it into a matrix profile and it becomes more significant. Those anomalies just stand out of the rest of the data sets. Those anomalies become very significant and it becomes very easy to separate them from the normal data. And it's like what it does, it's really magic how it does that. And it's very easy to also use. So you can try this whenever you are working next on your time series data set. Another applications of this particular example is that, so this is a taxi example. So the highest value, if you notice this data set, this belongs to the number of the hourly average of number of NYC taxi passengers over 75 days. So the hourly average of number of NYC taxi passengers over 75 days is this is the data set for that. Okay, and let's say if we convert this into a matrix profile, now this is what we get. Right now how can we interpret this in a way? So the first thing that you notice here is that every 500, after every almost 500, or after every 5,000, I guess, this is at 500, this is at 1,500, this is at 2,700 approximately, right? So after every around 1,000 1,200 data points, this pattern is repeated here, here, and here. So essentially, what can you make out of this repeated pattern? Here, you cannot notice any repeated pattern, right? From this red data, you cannot really understand if there is any pattern that is being repeated here. But when you see its matrix profile, you have a feeling that this is like a pattern that has been repeating. Now, what can you make out of this pattern essentially? What are your guesses? I want to know. What are your guesses on this pattern that is repeating here? What do you guys think? So essentially, I think that it might be a festival season, and on a festival season, there might be more taxi rides than normal, and the repeated behavior because we have though that we have the taxi season, or let's say we have that festive season thrice a year, and whenever there is a festive season, um, we have more number of taxis bookings in a way. Holiday travel, yeah, definitely. I'll share the presentation. Don't worry about that. Yeah, so that's one thing which is we will there is a repetition in this pattern. So whenever there is a holiday, there is an increase in the number of rides, right? We find the secondary peak around November 6. What could it be? Daylight saving time. So the clock going backward 1 hour gives an apparent doubling of taxi load, right? So we find a territory peak around 13th. What it could it be? It's a Columbus Day. So the respective peaks now they correspond to special days when there were offs, right? And that's why there is a peak in the number of rides. And these patterns we cannot really understand if we just look at the data that is there, unless we convert it into a matrix profile. Yeah. So matrix profile also helps us in understanding the patterns, the repetitive patterns or seasonality that there is. Yeah. So let's also focus on this power demand, right? So followed by the taxi example, this is the power demand of Italy from 1995 to 1998. Okay. So if you look at it, this red data that you look at it here does not really gives you anything. It does not make sense to us. It is just a lot of data, right? But when we convert it into a matrix profile, this is what it gets into. Now you see a lot of peaks, and what we can say is every peak actually, when you get into the details of it, you realize that every peak corresponds to a particular day. Every peak wherever there is would correspond to either a holiday or a let's say any public holiday or weekends or Xmas or something or the other, right? So essentially this is a very good way how we can analyze and how we can understand the data and clarify the noise from the actual meaningful insights. Make sense? Yeah. Similarly, there is another example wherein this is the ECG of a human, and you don't see any difference if you notice all this, right? Any difference? Here there is some difference, but you would not make sense out of it unless you create a matrix profile, and then you realize that there is some pattern here which is manipulating. Yeah, and this actually is a very interesting example, and let's focus here. What is this? So essentially, what these guys did is they recorded birds when they were doing their thing. They were talking to each other, maybe, so that they recorded their voice, and they created this is the red. The red data is basically the voice that they recorded for birds, and then they created a matrix profile. Now, interesting thing that they found out was that it is clear that this time series is not random. We did not expect the motive to be so well conserved or repeated so many times. This is evidence of a vocabulary and maybe even a grammar, which means that this is not just random anything that they are saying. There is definitely a pattern in there, and whenever there is a pattern, it means that some things are repeated in a way. In that data, things are repeating, and whenever things are repeating, whenever we conversate to each other, we repeat a lot of things, right? And there is a pattern in that conversation, and this is the evidence that there is a vocabulary when birds talk, and there might be even a possibility of a grammar. This is very interesting. I found this very interesting that how these guys analyzed a zebra finch bird and find out that there is something that actually they talk, and they don't talk random things, right? Okay. And there are many examples like that which you can maybe look into it when I share the slide with you. But essentially the thing is that the matrix profile can find structure in taxi demand, seismology, DNA power demand, heartbeats, however, the matrix profile does not know anything about its domains. It's not to it. So matrix profile essentially does not know about any of their domains. It just creates a pattern. It just creates some insights from that data set, right? So it is independent of the domain that it works on, and it works so perfectly on almost all data sets that there is, which is to find out some insights and some patterns in the data set. And this is the most beautiful thing about matrix profile. Yep. So having said that, I think that's the end of my presentation. I wanted to talk about matrix profile, and I hope I have shared some important insight regarding anomaly detection using matrix profile. So coming to your questions, matrix profile of a matrix profile. Matrix profile of a matrix profile could also give you another level of insights, and we can only see that once we do that. But it will definitely give some interesting insights. Thanks, Sachin. So seems like a second order differential. So second order differential does not have to be like this, and we can only find differential of continuous data. Remember, and whenever the data is not continuous, we cannot do the differential. And usually in time series, the data is not continuous in a way, if that makes sense. That was my thinking looking at the Finch data. Okay, that's interesting. Okay. What does Muhammad wear? Okay, seems like a second order differential. As I was saying, second order differential. So we do differentials of continuous data, right? And possibly in some cases, this could correlate to a second order differential, but I think this is more than just second differential data, and it can be it has more application than just doing a second differential on a data set. So why time series is not continuous? So in some cases, time series can be continuous. For example, if we record the temperature of a city for, let's say, 30 days, that could be continuous. But where it is not continuous is that wherein we record the sales of a particular company for 30 days, let's say, because sales happens in a way like, let's say a sale happened now, then the sale will happen, let's say, 2 hours later, somebody will buy a product, then let's say 3 hours later. So it's not continuous in a way, if that makes sense. Something that is not happening continuously, but temperature is there continuously, but sales of a product is not there continuously, if that makes sense. Well, how do you decide on the subsequent size for each case? Exactly. So I thought this would be the question that a lot of you might ask. How to decide the subsequence? I'm sharing this with everyone. I'm making this public, and even with the link in view. So that's a very good question. That how can you decide the subsequent size? So essentially, one way is to try different subsequences and see with which subsequence you get better results. Yeah, exactly, Timothy. So subsequence would be a more like a hyperparameter which we need to optimize. This is the only bottleneck that we have for this particular technique, that which would be how we decide that which would be the best subsequence. But I think it is comparatively easy in use. In most cases that I have used matrix profile, I've just tried with 2, 3, 4, 5, 6, 7, and usually it is one of these. It's never beyond 20, I would say. Never beyond 20 would be a good subsequence. But again, I'll have to put it there that it always depends upon the business use case that you are trying to solve. And there is a function. So the function, the library that you can use to calculate the matrix profile is Stumpy, STUMPY. And in this library, there is a function that can help you. It basically plots a distribution with various matrix with various subsequent sizes. What is the result? And it gives you a good distribution, and you can select that. You can see that wherever with what subsequence you'll get the best result from that visualization. But it takes a lot of time. That's a drawback. But you can definitely try this on small data. Okay, guys. So I've already shared the presentation with you guys, and I think it was insightful and interesting for you guys. If you have any more questions apart from this or anything else or any other projects that you have questions regarding, you can always ping me on LinkedIn. Happy to help everyone. So I think that was it from my side, and enjoy the rest of the workshops. Have a great day. Bye-bye. See you. Thanks, everyone. Thanks, Hasan. Bye-bye. Thank you, guys. Bye.